Okay, so now we're going to take a look at some of the uh, trends in metallic character, non-metallic character, and also um, how metalloids kind of fit into that relationship. So the first one we'll take a look at are the metals. And if you remember, on the periodic table, our metals are usually found on the left side, so over in this region here, and they actually make up the majority of the elements on the periodic table. All right, so we can say then that your metals, recall, are generally on the left side, the periodic table, and their properties, again, their characteristics, again, these are general characteristics. There are always going to be exceptions, but generally metals tend to be shiny. They tend to be lustrous. And then they also have characteristics of malleability. So if something is malleable, that means you can pound it into sheets. If you think of a aluminum foil, that's just a sheet of aluminum. And aluminum is a metal. It's very easy to do that compared to other types of elements. And then ductile means that it can be drawn into wires. So a good example of that would be copper that's easily also pounded into sheets, so it's malleable, and ductile can be drawn into wires. And it's used in electrical applications, etc. Metals also tend to be really good conductors of both heat and electricity, and that has to do with how the metal atoms are actually arranged, and what happens to the electrons that you have in a metal sample. And we'll just say this right now. We'll talk about this in more detail later on. The electrons in a sample of a metal are what are known as delocalized. So what happens is those electrons, the valence electrons, for instance, they actually are released from the metal atoms and they form sort of like a sea of electrons that are free to move around. And that then explains why they're good conductors of electricity, because you have these charges that can conduct an electric current. We also saw earlier on that your metals tend to have low ionization energies. Okay, that means it doesn't take a lot of energy to remove the outermost electron. As a result of that, your metals tend to form cations, right, which are positive ions. Because it's easy, in other words, it's easier to remove the outer electrons. It doesn't require a lot of energy to do that. So in terms of metallic character, what we are going to see, and we'll just do this in a general sense, metallic character increases from right to left. So again, that makes sense because metals are found on the left side of the table, and metallic character also increases when we go down a group from top to bottom. Okay, so in green here, we have metallic character increases. And then also going from top to bottom, metallic character increases as well. Right, and that's a similar trend we saw with the sizes of atoms, the atomic radius. Non-metals, on the other hand, are sort of polar opposite to the metals. So these tend to have differences in color, so they're more varied, in other words. They are not shiny, so they tend to actually be dull in comparison to metals. And instead of being malleable and ductile, they tend to be brittle. So they'll actually break if you try to pound them into sheets or draw them into wires. And instead of being good conductors of heat and electricity, these are poor conductors of heat and electricity. And we refer to those then as insulators. In contrast to your metals as well, your nonmetals tend to have high electron affinities. Okay, so our EAs tend to be high values, which means that these want to gain electrons. Metals tend to lose electrons very easily in comparison. So if your nonmetals want to gain electrons, as a result, these will form then anions, which again are negative ions, right? Because now we're adding, it's very easy to add one or more electrons to them. And as a result, they form negative ions. So again, sort of polar opposite characteristics for your metals and the nonmetals. The metalloids, on the other hand, right, these are located sort of intermediate between the metals and the nonmetals. So that little zigzag or the little staircase on the periodic table, we can draw a line. The elements that straddle that zigzag line, those are your metalloids, all right? So we'll just draw that line in. So you think about your staircase that kind of goes like this. Okay, those elements in green, those are your metalloids. And again, they're found between the metals on the left, nonmetals on the right, and we would kind of predict that they're going to have properties that are intermediate or somewhere in between those of the metals and your nonmetals. So for example, one important characteristic here is that instead of being a good conductor of heat and electricity like your metals are, or being a poor conductor, your metalloids tend to be semiconductors. Okay, and that's actually used in applications in electronics, right? So you think of pretty much any electronic device you have, a calculator to your cell phone to if you have a smart watch or something, these are going to rely on these semiconductors. A good example of this would be this one right here. So Si silicon is found in a whole host of electronics. Okay, so silicon, Si, not silicone, that's different. But silicon is a very widely used semiconductor. It's a metalloid. Sometimes you will see uh, another term being used interchangeably with your metalloids, and that term is semimetals. So semimetal would be another word, another term used interchangeably with metalloids. So the next thing that we're going to do is to take a look at how we can write the electron configuration for ions. Okay, so up to this point, we've looked at the electrons, looked at all the different subshells, orbitals, etc. We've been able to use the periodic table to configure the electrons in atoms. We've looked at a whole host of periodic properties, for instance. Now we're going to see how we can write electron configuration when we form these species called ions. So as a reminder, ions can come in two varieties. We have positive ions, okay, which we call cations. We have negative ions that we call anions. And what we're going to look at now is the electron configuration of what are known as monoatomic or monatomic ions. And we'll see some contrast to this in the subsequent chapters. Monatomic ions are ions formed from a single atom. So ions formed, or an ion formed from a single atom. So mono there meaning one. Okay, and just as a reference, this is compared to or versus polyatomic ions, which we'll see later on, which are things that have charges, yes, but they're collections of atoms. So we're going to focus just on these monoatomic ions. And we'll take a look, first of all, at the electron configuration formed of an ion formed by a main group element. Remember, a main group element is the same as the representative elements. Okay, and these are in groups 1A through 8A. So 1A, 2A, 3A, all the way over to the end. So the first thing that we need to do is to go ahead and write out the configuration for the atom. Remember, atoms by definition are electrically neutral to begin with. Okay, and then we can add or remove the appropriate number of electrons from that atom. Okay, to form the respective ion. So as an example, if we take a look at sodium, right? So if we find sodium on the periodic table, let's insert a periodic table here so we can use it as a reference. So there's Na, which is sodium, and right away we know that there are 11 electrons to configure. We can use our periodic table to help us figure this out. So we start with a 1s2, we go to the 2s2, 2p6, and then we have our 3s1. Okay, or we can write that, so that's the full electron configuration, or we can write the condensed form. So we find the noble gas that came before it. So we backtrack a second. Noble gas before sodium is neon. We put that in square brackets. Okay, and then that takes care of the first 10 electrons, and then we have the remaining 3s1. Okay, so we know then that that sodium being in group 1 and being a metal would tend to have fairly low ionization energies, and it will want to lose its outermost electron. Well, which is the outermost electron? It's the 3s1 electron. So this is the one that can be lost. And if we lose that one electron, guess what we end up with? We just take that away. We end up with 1s2, 2s2, 2p6, which guess what? Is the same electron configuration as neon. So what we say then is that the sodium species, the sodium ion that forms, which is Na plus, because now we've lost that one electron, this 3s1 electron. This is isoelectronic with neon. Isoelectronic meaning it has the same electron configuration. It's not the same atom, it's not the same element, obviously, but it has the same number of electrons, and they will be configured the same way. Okay, and we can confirm this just by looking at our charges, right? Sodium being in having atomic number 11. Okay, so that means it's got 11 protons, and it starts off with 11 electrons. Okay, so the overall charge here is 0. It's neutral to begin with. Now at the end, when it loses this one electron over here, guess what now? Well, now it's got 10 electrons, right? So now it's got 10 negative charges. Did we do anything with the protons? No, we don't mess with the protons. Okay, so they stay the same. Now we have an excess of one positive charge. So we compare the protons and electrons, we have a 1 plus, and that charge is what we introduce here as a superscript. That's our Na plus 1. Can leave the 1 in or omit it. It's not necessary in this case, is understood. So we end up with this Na plus cation, which is isoelectronic with neon. Okay, if we look at chlorine, okay, the electron configuration for chlorine, if you find chlorine on the periodic table, chlorine is over here, it's in group 7, 7A. It's got 17 electrons to configure. Okay, so if you write out the full electron configuration, it'll be 1s2, 2s2, 2p6. We have 3s2, and then we have 3p5, right? Remember, elements in group 7 have the ns2, np5 arrangement. That's the full electron configuration. We can also write this in the condensed form. Noble gas before it is neon. Then we have our 3s2, 3p5. Okay, so this is for the chlorine atom. Chlorine atom starts off with 17 electrons. Atomic number 17 has also got 17 protons. So the overall charge here is 0. It's neutral to begin with. So will chlorine want to lose or will it want to gain electrons? Well, we know that elements over on the right side of the table will have high values for their electron affinities. So the electron affinity values tell us then that these would want to gain electrons in this case. And in this case, the chlorine atom wants to gain one electron, right? Because we now want to fill this um, this shell, and specifically the subshell of the 3p, the 3p subshell, to completely fill it to make it more stable. So if we now gain that one electron, we end up with the same electron configuration as before. Now we add that one extra electron, that's going to go into the 3p to completely fill it. We end up with 3s2, 3p6. So now we've added an electron. Now it's got 18 electrons. Okay, it still has 17 protons. So if we compare these two, we have an excess of one minus charge. So we end up forming a Cl minus anion. Okay, and now hopefully what you'll see is that neon 3s2, 3p6, this is the same electron configuration as argon, the noble gas that came directly after it. So we can now say the Cl minus now is isoelectronic, has the same electron configuration with argon, the nearest noble gas. Okay, so generally, right, we can use these two as our examples. We can also make some generalizations. We can say metals tend to lose electrons. These form cations, positively charged ions. And then the opposite would be true for your nonmetals. When they do form ions, they will gain electrons. And as a result, they form negatively charged anions. Okay, these are two simple trends, or two simple sort of or straightforward generalizations, but it's really important that you kind of get that down, because we're going to use that a lot in the subsequent sections. So for the main group elements, we can determine their charges using their electron configurations. We can also use the periodic table to help us figure out what the charges are going to be. Okay, and we'll just give you a quick sort of snapshot of this right now, and then we'll come back to this when we get to the subsequent chapters. Okay, so for the main group elements, we can summarize this as follows. So main group elements or representative elements, we can say the charge on the metal ion is positive, okay, because they lose electrons, and it's equal to the group number that they're in. So for example, if I look at aluminum, okay, aluminum is over here, it's in group 3A, so that means the charge on the aluminum ion then would be 3 plus. Okay, it's positive because it loses electrons, it can lose 3 electrons to form a charge of 3 plus. Okay, so it's fairly straightforward for your main group metal ions. For the main group nonmetals, the charge in the nonmetal ion is negative, okay, and it's equal to the group number -8. So for example, if I have oxygen is O. If we find oxygen on the table, it's right here. Oxygen is in group 6A. Okay, so if I insert that as my charge, group number -8, group number is 6. 6 minus 8 is 2 minus. So I can quickly determine the charges on these, and then I can also determine their electron configurations using the technique that we talked about previously. So if you're actually given the charge and we have to come up with the electron configuration, it's sort of working backwards now, but we need to consider a couple things, okay? So if I look at N3 minus, if I'm given N3 minus, what this here tells me then, that the charge on it tells me if I have a negative charge, this means the nitrogen has gained 3 electrons, which imparts that 3 minus charge. Okay, so nitrogen, normally the nitrogen atom, if I look on the periodic table, okay, nitrogen over here has 7 electrons to begin with, to start with. So if I gain 3, we add 3 electrons, that would obviously give me a total of 10 electrons, okay? So if I try to configure this now, I have my 1s2, 2s2, and then my 2p6, add these together, okay, I end up with 10 electrons. This is then isoelectronic with 10 electrons. If I look on the table, 10 electrons would be the same as neon, so we can say that N3 minus would be isoelectronic with neon. Okay, so yes, you're adding negative charges, which would make the charge negative, right? So you want to consider these charges. If you're given something with a positive charge, that means you've lost those many electrons, right? So barium 2 plus then would be a barium atom that has lost 2 electrons. So barium, if I find it on the periodic table, right over here, it starts off with 56. If it loses 2 electrons, it'll end up with 54, and then it'll have a charge of +2. When we look at the ions that the D block elements form, right? D block elements, again, sometimes it's used interchangeably with the transition, right? Remember, you can see both those terms being used to refer to the same section of the periodic table, right? Which is going to be that big depression here in the middle. The case isn't that straightforward, so we can't necessarily use the group numbers for these to determine their charges. The thing you want to keep in mind is that the ions of the D block elements form when we remove electrons from the shell that has the highest N value. All right, so if you take a look at iron, for example, Fe, okay, so iron is right here. It's in the first row of the D block. It's got 26 electrons. So if we write the electron configuration for this, noble gas before it is argon. So we have Ar, right? Then we get to the fourth row, the fourth period, we have to go through the S block. So that'll be 4s2. Okay, remember when we get to the D is numbered 1 less than the 4. So we get to the 3D, we have to go across 1, 2, 3, 4, 5, 6 to get to iron, to Fe. So what actually happens with these D block elements is we actually lose the electrons from the highest value of N first. So if I have my electron arrangement, electron configuration for iron, these 2 electrons here, right, they belong to the highest value of N. These are the ones that are lost first. And guess what? There are 2 electrons here. So we lose those 2 electrons. Okay, so we end up with a charge of +2. We take those away, and our electron configuration then becomes argon 3d6. Okay, so this explains, or this here explains why many of the D block elements can form +2 charges. Okay, what you'll also see is that many of the D block elements can also form variable charges or different charges. And that's possible because now we can lose additional electrons from those D subshells, right? So for example, iron again, okay, it can form not just Fe with the 2 plus, it can also form Fe with a charge of 3 plus. So that means it's lost now 3 electrons. Well, we know the first 2 are going to be lost from the 4s. The next one has to be lost from the next lowest energy level, which is the 3rd energy level, specifically now the 3d6. So if we take 1 electron away, we end up with a 3d5 here as our remaining electrons. We've already lost the 4s2. We lost 1 of the electrons from the 3d, so we end up with argon 3d5, which will be iron with a charge of 3 plus. Okay, so this is very possible with your D block elements. They have variable charges, all right? And I think your book does a good job of sort of summarizing some of these charges here that you'll see. +2, +3 are the very common ones, but you'll see other charges as well. So if they lose two electrons. Those two electrons are going to most likely be from the highest N value shell. Okay, so in the case of iron, that was the 4s subshell. If there are additional electrons lost, they're going to be lost from the next highest energy subshell, which in the case of iron would be the 3d.